that one was easy, so no big deal. And then for this one down here, so we did number one and number two using logarithmic differentiation. So then you originally have x sine of x, and then you'd have to take the use natural log, which would get you, which would mean it's a or c at this point. And then but you have to take the derivative of sine natural log of x, and then that should be, or cosine natural log of x sine to the x, cosine natural log of x. And then that is plus sine x over x, right? Or am I wrong?
So you agree with the way I'm starting this?
Yeah, yes.
100%. Okay, so then from here you get dy over dx times 1 over y equals cosine x natural log of x.
Right.
Plus sine of x over x, which I think you said.
Yep.
Okay. And then, so then dy dx, you're going to multiply all this stuff by y.
So then, yeah, it'd be a. Yeah.
So x sine x times all that. Yeah, I agree.
Okay, cool. So I got that one done, 100%. Okay. And then moving on to the next one, if x to the third, so then we'll take the derivative. Yeah, we'll take the derivative 3x squared, and then dx, I guess, and then plus 5x dy dx.
So 3x squared plus 5x dy dx.
Yeah, and then plus 5y.
Okay.
Plus 3y squared dy dx. And then all that is equal to 0.
Okay, good.
So then we'll subtract the 3x squared and the 5y over to the other side. Negative 3x squared minus 5y is equal to 5x dy dx plus 3y squared dy. So then we'll basically just divide all of that, the other side by 3y squared plus 5x.
Yep.
And then that should be, and then at the points 1, 2. So then plug in your x's, which is 1, and then 2 for 5. So this would be negative 13 on top. Yeah, negative 13. And then 2, and then 13 on the bottom as well. No. Oh, wait, no. So then it'd be 4, 12, 17.
Yep.
So then it'd be C then. Yeah.
Yep.
Okay. Cool. And then for number 4, find the limit if it exists, 11x minus 1, 0 minus 1. So then we're going to do natural log. Natural log, all of that, if I'm not mistaken, right?
So let's say this. Let's say y is equal to this limit. All right, so what do you want to do to it first?
So we'll take the natural log of both sides, right?
So natural log of y is equal to the natural log of this limit.
And then because of the rule that states dividing, we can split them up. So then we have natural log 11x minus 1 minus.
So are we allowed to split this up yet?
Not
right
quite.
now. So right now, like, actually, these limits exist. Oh yeah, we can. Okay, keep going.
And then so we can split them up. Natural log 11x to the x minus 1, and that's minus natural log 2 to the x minus 1.
Yeah, right? So let me do this first. So the limit as x approaches 0 of the natural log of this thing, 11 to the x minus 1.
Okay.
But do these limits exist?
Fine. No, they
Nope.
can't. So then.
So we have to go back quite a ways because the, that second step there,
Mm-hmm.
this limit doesn't exist because
Oh, it's
numerator is going to go to 0, denominator is going to go to 0.
Gotcha. Okay.
So what do we do in that case where the numerator and denominator go to 0?
You'd have to take the derivative of that, right?
Derivative of what?
The function right there.
Just the, not quite. I mean, you do something involving derivatives, but it's not exactly the same thing as just taking the derivative of that. So you have this indeterminate form of 0 over 0. So you can use L'Hopital's rule. And the reason I'm kind of nitpicking you is because if you were to take the derivative of this function, that would involve the quotient rule. But what you really are doing is you're just taking the derivative of the numerator and the derivative of the denominator separately.
Okay. So
what is the derivative of 11 to the x minus 1?
it'd be whatever the derivative of x times the natural log of 11, right? Or e to the right?
I lost it. What did you say?
So it's natural log of 11. And then times, I don't remember the exact formula off the top.
Just times 11 over 11 to the x. So when you're taking the derivative of a
right, it's
of an exponential, the exponential part of it really doesn't go away.
Okay, so then, and then, yeah, that's that. Okay.
So now inside here, does this limit exist?
No. Wait.
You sure? What's
Yes,
11 to the 0?
Yeah, it does. It does.
Right. What is it?
11 to the 0 is 1. So, oh wait. Sorry, what did you say?
I'm just asking what the limit is.
Oh, natural log of 11. So it'd be 2.397.
Oh, let's just keep it as exact. I mean, all the answers over here are exact. So yeah, natural log of 11 over natural log of 2.
Okay. And then that's it.
So what's the answer then?
So then it'd just be C.
Yeah. So we didn't need to do this natural log step. I mean,
okay.
By the time we get here, we can, exponentiate both sides and we get this y equals natural log of 11 over natural log of 2. But the key for this one is realizing that you have this, this indeterminate form.
Right.
Which gives you justification to use L'Hopital's rule.
Okay. Gotcha. Okay, cool. So then moving on to number 5, find the f of x given natural log of x plus 2 to the third. Couldn't we take out that 3, move it to the front, so it'd be 3 natural log x plus 2? Yeah.
Yep, that is, yeah, if you got that, then this thing becomes quite a bit simpler.
So then it'd be derivative of natural log would just be 1 over x. Plug in the x to the bottom, so it'd be x plus 2. And I can already see the answer, and that should be D.
Yep.
And that one was significantly easier. Okay, moving on to numbers, I guess one of the free response for the function find the inverse function of f at c, in other words, f of 1. Okay, these are the ones that kind of confuse me, the inverse function. So
Okay.
do we take the derivative first and
Okay.
then we flip it?
Well, let's take the derivative and then we'll talk about it. So the derivative of this is what?
It'd be 3x squared plus 5x to the fourth.
Okay. Now we are really asking this. I want the derivative of the inverse at x equals 2.
Right. Okay.
So what's this equal to?
Give me a sec. Let me write some stuff down. 1 sec. I hate to admit it, but I don't know.
Okay. So it's 1 over f prime of the inverse of whatever our base point that we care about is. So we should know all this stuff now.
So then we're taking the
What is f inverse of 2?
That would be, would it be? Is it 6? I don't know.
So I'll give you this piece of information here. F of 1 equals 2. So what does that tell you?
So then it'd be 1.
Yeah. So yeah, f inverse of 2 is equal to 1. So what I'm really after is this 1 over f prime of 1. What's f prime of 1?
That would be 8.
Yep.
Okay. Can we, is there a way for, how do you get the inverse equation again?
So I have this theorem here. Let me have enough room. So basically the way that I built it up in class was this. So
because it's just the, yeah, it's reflecting over the XY axis. I remember that.
Oh yeah, so it's reflecting over this line y equals x. So if you have some function like this, and I'll try to replicate it.
And then it's the values basically switch, right? Yeah.
Yeah, because well, I mean that's kind of what inverse function does. So let's say this point right here is f, or this point right here is ab. That means there's a point on the inverse function called
BA.
BA.
Okay.
But what I'm really after is this. So basically we're going to generalize this thing we just did. I want to find, so over here my a was equal to 1. Was it equal to 1 or 2? So this is going to come out fine. So a is equal to 1, b is equal to 2. So I want to find what is the derivative of the inverse at this point A. Actually,
which can also just be written like you wrote it right there. 1 over.
Let's do B instead. So because in this way that I drew it, B is the input to the inverse, right?
Right.
So I'm going to draw a tangent line here, which didn't even come close to touching, but I don't care. So this right here is going to have a slope of, well, probably need to look at this one first. If I look at this tangent line, this is going to have a slope of dy over dx, right?
Right.
Which means this other one is going to have since I'm reflecting over this line y equals x, that vertical separation dy dx, if you reflect a vertical line over that diagonal line, this is going to become dy here, right?
Right.
And this vertical is going to become dx.
Yeah.
So I know that the derivative of f inverse at b is equal to dx over dy, right?
Right.
Which is the same as saying this, 1 over dy over dx.
Right.
But how did I get dy dx? I got that from f prime of what? Of a. Oh, sorry. Well, I messed up.
Of b?
No, it should be 1 over f prime of a. Because basically, that tangent line here on the bottom, that's where I got my dy dx from.
Right.
So that's what the derivative is equal to at x equals a.
Okay.
So are you with me on the 1 over f prime of a?
Yeah. So
Okay.
I'm with you.
Okay. So this is all correct so far, except, the whole point of this theorem is that I don't have to look for different inputs. So I started this thing off by talking about b. So I want to end it talking about b. So how are a and b related? Well, I know that f of a is equal to b, which means f inverse of b is equal to a. So I'm going to write this a as the 1 over f prime of f inverse of b.
Gotcha. Okay, that makes a little more sense now.
Yep.
Okay. And are we ever gonna? I think we are. Was it on the homework where we were asked to write the inverse equations of what was originally given?
You mean like the inverse function here?
Yeah.
So the whole reason for the inverse function theorem in this case is that this inverse is either very difficult or impossible. I think it can be done, but
so we're never going to be asked to actually find the end.
I mean, if you could find the inverse, you wouldn't need that theorem.
Right. But but in these cases, I'm guessing maybe on the test. I highly doubt it, but maybe on the test. We might.
I mean, the inverse function theorem might be on the test. It's something we've definitely talked about. But remember, the real use of that theorem is when functions are hard to take it, when the inverse is hard to find. So, like, for example, I could ask you, all right, here's f of x equals, x cubed minus 1. And I could ask you for, all right, what's f inverse prime of 5?
Mm-hmm.
You could use the inverse function theorem on that, but it's also really easy just to invert that. You could find f inverse as, what would that be? The cube root of x plus 1? Cube root.
Yeah.
So in cases where you can just find the inverse, I mean, you could just take it, and then now that you have the inverse, you can just take a derivative and plug in whatever value you want. So the real usefulness of the inverse function theorem is for functions like this, whose inverses are really hard to get to.
Okay. And so, I mean, couldn't you do the inverse function theorem on that one as well? But it probably
it's so long as the function is continuous and has an inverse, you're absolutely allowed to use it.
So then in that case, for the easy one, we would set whatever is, we'd set the x equal to 5, right? For the first one? And then solve it, and then that would
so
be,
yeah, for this one, you could do, f inverse. If I wanted f inverse prime of 5, then I would do this 1 over f prime of f inverse of 5.
Right, and so that would be,
and then f inverse of 5 would be something silly like the cube root of 6.
Right.
So I mean, yeah, you can definitely use that theorem there.
Okay. Cool. Well, yeah, those ones confuse me, so I'll have to go back and
Yeah, I
look
mean,
at
it's kind of it's a strange theorem to think about.
Yeah.
I understand it a lot better now than I did before the semester started, just by having to really wrestle with it well enough to teach it.
Yeah. Okay. And then that one's awesome. Moving on to number 2, $1,000 is less than annual interest rate compound. The amount years is given. So I thought this was just a plug-in, but
No, not quite.
there was more to it than that because I was
Yeah.
trying to
So
do different things.
let's talk about this. What is this function A? What does this function describe?
So it's just basically saying it'll give you a final amount after the 4 years, depending
Final
on
amount of what?
Money that you have.
Okay.
Invested, yeah. So it'll give you a final amount that you have depending on your percent increase or your compounded percent increase.
Yep.
After the 4 years.
Okay, so R is just some interest rate, right?
Right.
And then A is the amount of money after 4 years at R%. Like, it's not R%, you got to convert that. So what are you being asked to find?
So it's from I'm pretty sure it asked you find how much money you had at the beginning and find how much money, the rate of change. So find how much you had at the end. So then originally I thought you have 0 and 1,000, and then you'd have your percent, which I thought you just plugged in 0.04.
So it sounds like what you're describing is, so keep in mind the variables for this thing are R and A, right?
Right.
Time is not a variable here. So the change you're looking at, the change you're looking at has nothing to do with, you said beginning and end. But if I'm looking at this function, the way it's defined, time is not part of this. This function is only written to tell you something about what happens in this account after 4 years.
Right.
So talking about it in beginning and end is that you're kind of attributing stuff to this function that's not really there. So you're asked to find the rate of change of the amount A with respect to the rate R. So what is the language of that question they're telling you?
So just find out how much money have you had increase with respect to your percent compounded, right?
Well, I mean, I don't just want, there's a difference between the increase and the rate of increase.
Okay, so then.
So, for example, let's do this. Let's find A of 4. So if I calculate that out real quick, or I guess it should be not A of 4, but A of 0.04.
Should be like 16, close to 16. No, not 16.
So 1,000 times 1 plus 0.04 over 12, all raised to the power of 48. So I got this down into the penny, 1173.20.
Yeah.
So what that tells you is this: when the interest rate is 4%, this account will have $1,173 in it, right?
Right. So then I thought, okay. So then I thought, don't you take that, subtract the original amount, and then divide that by 4 to find out your rate of change over the 4 years?
So let's think about what we do that. So if you take 1173.20 minus 1,000 and divide it by 4. First, let's get our numbers. We can talk about what that number means. So that's 43.29 or 43.30.
Yeah.
So that equals 43.30. Can we assign a unit to this thing?
I guess you can make, I don't think so, but you can try calling it increase of amount.
Well, I mean,
Amount per year.
so look at what we subtracted.
Average.
Look at what we subtracted. 1173.2 and 1,000. What are those both measured in?
Dollars.
Those dollars, right?
Yeah.
What's
So
the numerator?
average,
What's the denominator measured in?
years. So then
Okay.
dollars per year.
So this is a rate of change of dollars per year, right?
Mm-hmm.
Average rate of change of dollars per year. That is not the rate you are asked to find, because that, dollars, yeah, that's a measurement of A.
But there's no measurement of R then.
Yeah, years is not a measurement of that interest rate.
Okay.
So you are asked to find a rate of change of the amount with respect to R. So basically what they're asking you is this, not what happens to your money after 4 years. They're asking basically, all right, if I were to alter the rate a little bit, what would that do to how would that affect how much money I get?
Okay.
So I want to know how the bank account responds to the interest rate, not how it responds to time.
Gotcha.
And really, this function here, this is A as a function of R. So that's really the only instantaneous rate we're going to get.
Okay.
Right. So how do I find how do I find that the rate of A the rate of change of A with respect to R then?
So then would you have to solve? No. Do you have to solve for R?
How would you do that? I mean, let's think of it. You're asked for a rate of change, right?
Right.
What does that phrase evoke? Like how do we find rates of change?
It's from measuring from one point to the other.
Well, that's an average rate of change.
Well, then
in this case, I want an instantaneous rate of change. How do I get those?
Then you'd have to take the derivative.
Okay. If I took a derivative of this function, what would a good name for that derivative be?
Good name.
This notation.
DRDA?
Not DRDA. Usually we have something like this, right? Y equals 3x squared plus 9x or something like that.
Oh, so then it'd be dA over dA.
Yeah, because I'm taking the derivative. So in this case, I usually have taken the derivative of y with respect to x. Y is a function of x. In this case, A is a function of R. Right, so if you just take that derivative there, this is going to give me an instantaneous rate of change of A with respect to changes in R.
Okay, so then the derivative would be 4,800, or wait, 48,000.
48,000.
And then times 1/12.
Times what?
1/12.
Times 1/12.
And then times the inner function, which is just 1 plus 1/12R to the 47th. Oh.
Yeah.
Okay.
So once you have that, then you set R equal to 0.04 and you got it.
Dang it. Ah.
So yeah, I mean, it's just that was a conceptual thing. I mean,
So yeah, I was just thinking of average rate of change instead of the instantaneous.
yep.
Okay. Ah,
Memory, sir. Oh, you got the answers in front of you, don't you?
yeah, I do.
I
Yeah.
think it was like something like $4,000, something like that.
Let me check right now.
$4,000 per percentage point.
Yeah, 4,677.
Yeah, that sounds familiar. Okay.
Okay, that one was wait, I should have had that one. Okay.
Man, I think the mathematical computation to do there is not hard. What is tricky is figuring out what I'm asking you for.
Yeah, that if
mean,
it doesn't have those keywords, I kind of get confused, as you can tell.
Well, I mean, the key word here is if I'm asking you for a rate of change, and here's the thing, I'm asking you for a rate of change with respect to one point, right?
Yeah.
So if I ask for if I gave you R, so from R equals 4% to R equals 9%, that gives you like that connotes like an average rate of change. But in this case, I only care about that R value.
Gotcha. Okay.
So yeah, the only way to get to the rate of change that is involves one input to your function, that should scream at you derivative.
Okay. Gotcha. Well, that would have been, I just need to look for the context clues because that was very easy after I knew what actually to do. So,
and I think the reason that one was hard is because, we've talked a lot about derivatives with rate of change, and very, very commonly, not just, just in every context, very, very commonly, the independent variable is time. Okay. And it wasn't in this case.
Gotcha.
All right.
Okay, so moving on to this one, we'll find the derivative, which is 2x plus 3y squared dy dx is equal to 0. Subtract the 2x, so that'd be negative 2x over 3y squared. That would be our derivative. And then it's talking about dx over dt is equal to negative 3 when x is negative 5 and y is 2. Was this asking for a double derivative?
Not really. But here's the thing, you're being asked for dy dt, right?
Right.
So a couple of different ways that you can handle this. So I think just by default, like what we usually do is differentiate with respect to x. And the way you did that here was perfect. The problem is it's a little hard to, do you understand how dy dx is related to these things, dy dt and dx dt?
Not 100%.
Okay, so here's what I would advise instead. You want this dy dt thing. So instead of differentiating with respect to x, we can differentiate with respect to t, to time.
Okay.
So I'm going to differentiate both sides of this thing.
In terms of dt. Okay.
Yeah. Because we're so used to thinking of y being a function of x, and it definitely is in this case. But what I'm also telling you by telling you that dx dt is equal to something, and asking for dy dt, is that x and y are both functions of t.
Right.
So based on that, what would the derivative of x squared be with respect to t?
2xt.
Well, here's the thing. So I'm using t to make functions, right?
Right. Okay.
So one of those things, I don't know what the function looks like. I don't really need to know, but I know that t is going to do something and turn into x, right?
Right.
It's also going to do some other thing
Turn into y.
Turn into y. And then specific to our cases, that x is going to go through this process, which is going to square it, right?
Mhm.
And the y is going to go through this thing, which is going to cube it. So it's a little tricky, but when you write variables in terms of other variables, you're really, you're composing functions. There's some function that translates t to x. And there's a more obvious function that translates x to x squared. Does that make sense?
Kind of, yeah.
Okay. So really, I don't know. Like, there's a function out there called x of t, and I don't know what it looks like, nor do I really care about it. I don't need to know exactly what it says.
Right.
And the reason I don't need to know what it says is this. So we're going to use the chain rule, right? So we're handling the x term. So the first thing we're going to do is to differentiate x squared with respect to x, right?
Right.
That's how you got 2x. But then chain rule says we got to, go from the outermost function to the innermost. I don't know what the function is that turns t into x. But what is the derivative of x with respect to t?
Just one.
No, it's probably not just one. That means if it's one, then you would need x and t to be the exact same thing.
Oh, 1t then?
Not quite. So I'm looking for the rate of change of x with respect to t. I don't know what that is, but I do have a name for it. I can call it dx dt.
Oh, okay. So then for the y one, it'd be 3y squared dy dt.
Yeah.
Okay.
And then the derivative of 33 with respect to anything is 0 because that's a constant.
Right.
So from here, you basically know everything except the thing you want to solve for.
Okay, and so then you want to get let's just say dx over dt equals -3.
Mm-hmm.
X is 5.
Yeah, so 2 times 5 times -3 plus 3 times 2 squared times dy dt equals 0.
Right. So then, okay, yeah. So then you'd get -30 plus 12 dy dt equals 0.
So dy dt is equal to
30 over 12.
30 over 12, which is
20 or 2 3/4, right? Yeah, 2 3/4.
Yeah.
Okay, I see.
Okay.
So yeah. Gotcha. That one makes sense.
I don't think that's right. So 30 over 12 is...
Wait, 6 12 or 1/2. Sorry.
It's not 1/2.
Yeah, 2 and 1/2. 2 and 1/2.
Yeah, 5 halves. All right.
Okay. Yeah, that one makes a little more sense once we're explaining it.
Good.
And we only got 2 more. So then find the derivative. Derivative of 11e to the x is just 11e to the x. Oh, minus x to the e. Isn't that just, yeah, it's not, that's natural log of x. X to the e?
No, it's not going to be a natural log. So, I mean, x to the e, right? So the base is constant. The base is variable. The base is x, right?
Right.
The exponent is constant. So basically what you have is you have this x to the n thing, right?
Mm-hmm.
So this is essentially just power rule.
So it's just x to the e plus 1. What? No. Minus 1.
Oh, not quite. I think you missed something here. If it was x to the 6, what would the derivative be?
5x to this, or yeah, no, 6x to the 5th, sorry.
6x to the 5th. So then what's the derivative of x to the e?
Ex to the sum 0. No, it can't be 0, 1.
No. What did you do to the exponent over here when you took the derivative?
E minus 1.
There you go.
E minus 1. Okay. And so then you can just plug in for x, right?
Yeah, so f prime of 3 equals 11e cubed minus e times 3 to the e minus 1.
And
which is like 200 something from what I remember.
I got the number right here. This is number 4. Yeah, 202.99.
Yeah.
Okay. Gotcha. Okay.
So yeah, I mean, just one, the powers aren't always going to be, whole numbers or rational numbers. They might be something strange like the power of e, but as long as the exponent is constant, you can just apply power rule to it.
Okay. Gotcha. That makes sense. And I think this is the one I actually got correct, full credit on.
Okay.
I studied hard on this one. So I set up my cube first.
Okay.
And then the edge of a cube was found to be 40 centimeters with possible error measurement of 0.01. Use differential assess 70% error in computing the cube. So then one side is 40, and then we take the volume of the cube,
Okay.
And then we take the derivative of that.
So what's the volume of this thing?
Whatever the side is cubed, right?
Yeah.
So yeah, x cubed. And then take the derivative of that. So it's 3x squared. And then we would times that by dx, which would be the 0.1.
Yeah, so here's in terms of differentials, basically I'm trying to find dv, or among other things. So what do I do from here?
So then can't you plug in everything? So then you have 3 times 40 squared times 0.1. And then I first solved for that, but you then have to solve for what is the expected without a percent error or possible error.
So this right here is going to be 1600, 4800, 480. Yeah. So dv is equal to 480.
Right. And then
if we find the nominal volume,
40 cubed would be 64,000.
Okay.
So then, if I'm not mistaken, is it 480 times 100 over 64,000?
Yeah, so basically, here's my error. My possible error is 480 cubic centimeters out of a measured 64,000 cubic centimeters.
Okay, yeah.
So that will give you some ratio, but if you want to make a percentage, you got to multiply by 100%.
Okay, so you don't multiply 480 right away then.
I mean, you can.
Oh, okay.
I think this just makes more clear why you're making the calculations you're making. So 48 over 64 is
so your percent error would be something like 0.75, right?
Yeah, that sounds familiar. So 0.75%.
Yeah. Okay. Yeah, that was the one I was super confident on.
Good.
Okay.
And
so
of the tests I gave, that one like pretty significantly had the lowest average. So yeah, hopefully it makes sense.
Yeah, no,
what we talked about here.
Going through everything again definitely kind of not only refreshed a lot of things, but kind of made me realize that I have to look more into depth about the problem for context clues. Because as soon as I know what like the specific thing, like if it would have said instantaneous rate of change, would have knew exactly what to do. I just need to pick up on that sort of stuff.
So let's talk about that. This number 2 here. What about, so I didn't use the word instantaneous, but what about this tells you that it has to be instantaneous?
Well, like you said earlier, it only gives you 1 point instead of 2 points. Because if it gave you like something, I think you said 9 and 4%, then you imagine you find the average. But
if I ask you for the change over an interval, then that's by definition an average rate of change.
Right.
But this case, that interval consists of one value.
Right. Okay. Cool. Well, I think I'm gonna take like a 10-minute break. I'll be back like at 4:10. You're gonna still be here until 5, right?
Yeah.
Okay. So I was planning if you wouldn't mind to go over just test 3, all of it, unless you have like specific stuff you want to discuss. But
no, it's totally up to you.
Yeah, I was planning on just kind of going over test 3 next because I feel like test 1 was pretty easy, basic stuff.
Okay.
But I'll be back in like 10 minutes just to get out, walk around, get some water and stuff. So
sounds good.
Okay. Okay, so I'm back. Sorry, it took a little longer than expected.
There you go.
Okay. So yeah, if we can, I don't have the exam 2 or exam 3 questions. I don't think they're been posted.
No, I didn't post the actual exams, but I can pull it up.
Okay. Yeah, and I guess since it's relatively new, we should be fairly quick. And if we have time, I guess we can go back to exam 1.
Okay, it's up to you.
Yeah.
All right.
Okay. So.
Oh, this is 2. Sorry. Or
Okay. So evaluate the integral below. So this one is just doing the 3 minus absolute value of x minus the 3 minus absolute value of -3. So then it would, what, I think I just put what it was. So it'd be 3 minus, wait, no. So we'd find the antiderivative first, right?
can't really do that with absolute value. So remember, it says, if you read this, it says to interpret it in terms of area.
Right. So then it'd be 3. Don't I have this? I have this somewhere. Wait 1 sec. Here we go. Okay. Oh, that's right. I had to graph this one. This is one of the ones where you had to graph it, right?
Yeah, I mean, the derivative is not something you can get to easily.
Yeah. So then,
I mean, in fact, to take the antiderivative, you need to split this up into 2 different integrals. But yeah, it's probably simpler to graph this.
Yeah. Okay. And so then I basically, what I did on my calculator was looked at the points where it was 0. And luckily enough, those were 3, 0 and -3, 0. And then I found that the height or the limit was 0, 3. So then it's just 1/2 base times height.
Yep.
So then the base is 3. Height is 3. Yeah.
Base is 6.
Oh, base is 6. Yeah, my bad. And
Yep.
then height is 3. And then so that would be 18, but then you have to divide it by 2. So then you got 9.
Mhm.
And the next one was pretty easy. The multiple choice on this was pretty easy. And so it's just 0 to 7. And if you just take out the 5 to 7 part, you just get 0 to 5.
Yep.
Okay. And then regarding the next one, now I'm going to put people there. We just need that. So then on the intervals -1 to 3, find the values of the conclusion of the mean value theorem. So this one, we find the antiderivative, right?
No. So what does the mean value theorem say?
This is the one. Okay. It was the rate of change, right? It's like, no, wait. Am I thinking this wrong? I think I'm thinking about this wrong. What's the formula for this one? It's f of 3.
I mean, let's just, what does this theorem say?
It's just it's finding the area under the graph.
No. So a mean value theorem basically says that, if you have some function over an interval, so whatever the slope is between those 2 points, Like if you take the average rate of change over some interval of a continuous function, the function will, somewhere have a derivative that's equal to that. So if you have a function that's continuous and differentiable over an interval,
Right.
then its average rate of change and its instantaneous rate of change will be equal somewhere.
Okay.
So for this, basically, let's find the average rate of change over that interval. So what would our average rate of change be?
So being 10 over 3 or 10 minus or 10 minus 2 on top, and then over 3 plus 1.
Okay, so that's
2.
Average rate of change of 2, right?
Right.
Right. So how do we find where the instantaneous rate of change is equal to that?
You would just take the derivative and plug that in.
Okay, so what's the derivative?
2x.
Okay.
And then you'd have to make it where f prime of x is equal to 2.
Yep, there you go.
And then divide by 2, it's just 1. So when x is 1, that's when you get your average. That's when your, I guess, your instantaneous rate changes your average, or right?
Yeah. Yep, because so f prime of 1 is equal to 2 times 1, which is equal to 2. So yeah, at that point, the slope of the tangent line is parallel to the the slope if I were to just connect those 2 points.
Okay. So what I was thinking of regarding the antiderivatives is finding the area under the curve of that interval, right?
Yeah. So yeah,
Right.
that's a completely different thing.
Yeah. Okay. I just, because I did those problems. I did a couple of those problems. What was it, last night? So it just
Gotcha.
looked very similar. Okay. And then the next one, estimate the area 2 decimal places under the curve from x to 1 using 4 rectangles and write endpoints. So this one I like to do, just formulate it. So it'd be 0 to 1 decimal, the values that were given. And then it'd be 1 minus 0 over 4, which would give us 1/4. And so we're going to be using the points 0. We have the points. I shouldn't say we're using. We have the point 0, 0.25, 0.5, 0.75, and 0. And then 1. So we have those points. And then we take the, I don't want to say the wrong thing here. Okay, and then we set it up. So at least the way I do it, it's 1/4 times sine, and we're doing right endpoints. Yeah. So it's 1/4 times sine 0.25 squared plus sine 0. Yeah. I just, it's just easier for me to understand.
Yep.
And then 0.5 squared, and then sine 0.75 squared, and then sine 1 squared.
Yep, okay. That's it. And then I think this comes out to like 0.42 or something like that.
Yeah. I have it right here. Yeah, 0.42115. So yeah. I feel like this is going to be a little, I shouldn't say difficult. It's just I have to pay attention to what should be antiderivatives and not, because everything with dealing with integrals.
If it helps you here, draw what's happening, even if you don't know what the function sine of x squared looks like.
Mm-hmm.
You're asked for area, right?
Right.
And you are basically splitting up into 4 rectangles. However, as I'm using right endpoints, how are you finding the heights or how are you finding the bases and heights of all these rectangles?
The length times width.
Yeah,
Oh.
but how do you get the length and width?
From the b minus a over n.
Okay.
Then,
So that's the base. How do you get
and
the
then
height?
you're just plugging, and then you're just plugging in the number for where it is
Right.
on the graph.
So in this case, like you don't want the derivative or the antiderivative. You just want you just care about what the function is.
Right.
That's why. I mean, so my advice would be, I mean, if you can try to draw a picture to somehow, organize this for yourself.
Okay.
But yeah, in this case, you don't care about the you don't need to differentiate or anti-differentiate. And with the previous one, it sounds like you're not quite sure what the mean value theorem is. So I would just review the, make sure you know what the definition of that thing is.
Right. I think that was what, chapter 3?
I think it's somewhere in 4. I think early in 4.
Oh, okay. I thought it was late 3. Okay. Gotcha. Cool. So the 2 is pretty self-explanatory, pretty easy. And then given that f of x is equal to 2, so wouldn't it just be 2e of x?
What's that?
Given that f of 1 is equal to, or f prime is equal to 2e of x and f of 0, 6, find f of x. Oh, okay. So we have the derivative of this, derivative of 2e to the x is just 2e to the x. So it'd be f of x is equal to e to the x plus c. Yeah, okay. That's why that 0 is in there. And then you make that equal to 6. Yeah. And then I think once you do everything, it should be like 3, 4, or 5. I don't remember at the top of my head. Something like that.
Based on what we have.
Yeah, before then. Because each of the 0 is 1. Yeah. Okay.
So yeah. 2 to the x plus 4.
Okay. Yeah, that one's pretty easy as well. Particles moving on a straight line and has acceleration. So this is the one where we take its acceleration is 60. Yeah, this is where we take two antiderivatives here. So first, the antiderivative of 6t squared plus c.
Not 6t squared.
Or 3t squared plus c, and in position time. So then equals 12. So then it just be, so c is just, yeah, c would just be equal to, t would be equal to 0. So c would just be time. Wait. Oh no, I was looking. Okay, no, wait. You have to do the VO equals 8 first because this is velocity. This isn't position is the last one. So then we'd have 8, yeah. And then the antiderivative of that would be 3 over 3, or 3t cubed over 3 plus 8t plus c. And then you'd set that one equal to 12.
Okay.
And I'm pretty sure you get 12 for that one.
Yeah.
So then, and then regarding what is its position at t equals 5, you just plug 5 into the equation and you should get something like 177. Okay.
Yeah.
Gotcha. These ones are fresh in my mind, so these are easier than the last.
Okay.
And then suppose that f of x is equal to 2x e to the x, use interval notation. Okay. This one was confusing one. So for this one, you have to use the product rule, right?
Mhm.
So it's 2 times e to the x, and then plus 2x e to the x.
Okay.
And so since we're looking at concavity, we also have to take, I took the derivative again.
Yeah, you have to.
So then you'd have, should be the same thing, 2e to the x, or 2e to the x plus 2e to the x, and then plus 2x e to the x.
Yep.
Okay. Is there any way to combine that, by the way?
Yeah.
So could we say 2 or 4e to 2x?
No, just 4 to the x.
Okay. Plus 2x e to the x.
Yep.
And so then, yeah, this is the part that tricked me up. You set it equal to 0. But what else? How would you get it a number on that side?
So you can factor this.
So take out, oh, I see. Take out an e to the x. Take out an e to the x, 4 plus 2x. Okay. And then you get negative 1. And then for
Negative 1?
Or negative 2, sorry.
Yeah,
2.
negative 2.
And then for e to the x one, would you have to take the natural log of that, I'm guessing?
What happens when you take natural log on both sides here?
It gets rid of the e.
So you got x equals the natural log of 0, which is what?
I don't think you can do that.
No, you can't. So, and think about it this way, e, you can't raise e to anything and get 0.
Right, okay. So then it'd just be...
Yeah, the e to the x cannot equal 0.
So then that's our inflection point, correct?
Yeah, well, possibly. You got to make sure now you just got to check the concavity on either side of this thing.
Okay. And so to check for maximum and minimums, we set couldn't we set the first derivative equal to 0?
I don't want maximum. I don't want those. But yeah, you could. I'm not asking for those here.
Okay. So then you can set it up in I guess the line type of format where we have negative 2. And then we'd probably want to look for just negative 1 and negative 3, I'm guessing. Because dealing with decimal points seems not too well. And so we just plug in negative 1 into the original equation.
I suggest using 0. So whenever you have the chance to use 0, it's simpler.
Okay. So we put 0.
So we know, what are we looking here? So we got these test points. But what am I plugging them into?
The original derivative, right? I mean, not the original derivative, the original equation.
No, what am I trying to find out?
Whether they're negative or positively increasing. So then it'd be the double derivative.
Yeah. So yeah, I'm looking for a concavity. So that comes from the second derivative. So another second derivative at negative 2 is equal to 0. Now I got to figure out what's happening at f double prime of negative 3. And that's equal to 4e to the negative 3 minus 6e to the negative 3. Is that positive or negative?
That is negative.
Yep. All right. And how about f double prime of 0?
That should be positive. Oh, wait, no, negative. Sorry, negative.
I think it should be positive. So 4 e to the 0 plus 2 times 0 e to the 0.
Oh, yeah.
That's 4.
Yeah. I was looking at the -6. That's my bad. Sorry.
Oh, okay.
So then, yeah, so then it'd be a concave up from -infinity to +infinity, right?
No, it's not concave up everywhere. We definitely found a negative number for f double prime of -3.
So then what? Wait, so if it's not concave up everywhere.
Well, I mean, so look at this number line we made. The whole point of this was for us to figure out, so we know that at x equals -2 that we have no concavity.
Right.
Second derivative is equal to 0. But to the right of that, we have that the derivative or the second derivative was positive. And to the left of that, we had the second derivative was negative. So what does it mean if the second derivative is negative?
It's concave down.
Yeah.
So then it's concave down from -infinity to -2.
Mm-hmm.
And it's concave up from -2 to +infinity, correct?
Yeah. Yep.
Okay. So then this was a weird graph. I remember this being a really weird graph.
Yeah, probably is.
It was like, because I thought, yeah, no, that's right, because it's when the inflection point is when it switches concavity. It's not.
Mm-hmm.
Oh, okay, yeah. No, I was thinking of maximum and minimums. That's
yeah, it has a minimum at like x equals -1.
Yeah, no. I wrote that down. The
right.
code points out -1. No, I guess I was just thinking about the maximum and minimum because I know that's a way to find whether it's concave up or concave down. But okay, yeah, this is the inflection point I have to remember. Okay.
Yeah, so the second derivative test can tell you something about max and min values, but I don't really even care about the max and min values here.
Okay. Gotcha. Oh, and by the way,
yeah,
I want to make sure. Do I have to write? Because I know I got marked. I know me and a couple other people got marked off for this. What was it on problem? When we were writing our absolute mins and maxes, I have to make sure that I write them in.
Yeah. So this very last one.
Yeah, that was the one I just wrote.
Yeah, I mean, if I want the location for something, I want the full location of it.
Okay. Gotcha. Okay, I just wanted to make sure for the test that I knew that. Yep. Okay. Cool. So then going on to number 6, I knew this was the only reason I was able to get as far as I did in this one was because I remember this being a homework problem. I don't remember. I remember they did that. That's the most I wrote in the paper. It was AB is equal to 64 because it's the product, and whose sum is a minimum. So it's A plus B is equal to some number. And I remember it was 8 because that was what the homework were called. Okay. So honestly though, I don't remember what else to do from there. I kind of went in blind.
Okay, so I mean, usually the tough thing about these optimization problems is trying to figure out like the equations for the thing you're trying to optimize and whatever constraint or limit like you have. Mm-hmm. You just told me those two things though. So which one of these things am I trying to optimize?
It's the A plus B equals S, right?
Right. So I'm trying to optimize this.
by getting the minimum possible.
Yeah. And this right here, I'm trying to, this is my constraint. But since you have both of these, now what?
So then you can solve, you can get either A or B alone. I'm not sure which one would be better.
Don't think it matters.
But then you'd get basically S or B or A is equal to S minus whatever the other one is.
Well, I mean, let's solve for one of them. From AB equals 64, you got to solve for one of them. Doesn't matter which one though.
Oh, I thought we had to do for the optimized one. Okay, so then it'd be A is equal to 64 over B.
Okay. So keep in mind the one you're going to optimize, there right now there are 3 variables in there.
Right. Oh, okay. Yeah.
So and remember, you're trying to optimize something. In this case, you're trying to find a minimum. Sometimes you're trying to find a maximum. But if you're trying to find a minimum or a maximum, what do you have to do? Like if you're trying to find the minimum or the maximum of function, what do you have to do to that function?
You have to find one of the parts to the function, right?
What do you mean by that?
Whether that be A or B or whatever you're trying to find.
Well, I mean, I just mean in general, where do maximum and minimum values of a function happen?
When it's 0.
When what 0?
The slope.
How do you get slope?
Derivatives.
Right. So, and it's the thing I want to optimize. I'm eventually going to have to differentiate. So I want to differentiate this sum equation. But before I can do that, I need to express it in terms of a single variable, which now we can do. So now I got S equals 64 over B plus B.
Okay. And so then that's 6. So then we still have, but we still have 2 unknowns. So
well, I mean, functions are always in 2 variables though, right?
Mm-hmm.
So this should be okay.
Okay.
So if you're going to differentiate, so this function, capital S, you're going to differentiate that with respect to what now?
With respect to B.
Right. So we're going to find ds dB. So the problem was before you had a function in 2 variables. It's not something you know how to do a derivative of yet. So what is ds dB?
Ooh, would this be 64 natural log of B?
No, that's the antiderivative.
Okay. So it'd be, it'd be, I'm trying to think of the 64 over B, and then it'd be plus 1.
Mm-hmm.
But 64, what's the rule where if you have the numbers on the bottom, because right now I'm thinking about it when it's in 64 beats the -1,
mm-hmm.
and you add 1 to it, it becomes 0, but you can't have that. And then I thought that you could write but
that's an antiderivative. That's not what you're trying to do right now.
Right.
So treat this like you would power rule for derivatives.
Okay, so it'd just be -64b to the -2.
There you go. So
the antiderivatives.
-64 over b squared. So now that I have that derivative, what do I want to do with it?
Then you want to plug it back into the original equation? No, you can't do that. Would you plug it in for A? No, no, no. I don't know. I don't know.
So what are you trying to do? Like, what are we trying to find here?
Oh, make it equal to 0.
Right. Okay. Set this equal to 0. So that gives me 64 over b squared equals 1.
And then you subtract the negative 64 over. Or,
Oh, I mean, I've already, yeah, I've done that. So that's where that 64 over b squared is equal to 1.
So then you'd want to multiply by b squared.
Mhm.
And
So that gives me
then
b squared equals 64.
square root both sides.
So b equals 8.
Couldn't it be positive or negative though?
Nope, I told you this was two positive numbers, so I can ignore the negative. So if b equals 8, what does a equal to?
Then it must be equal to 8 because you can just plug that into the AB equals 64, and then that just divides by 8.
All right, so the last thing you need to do is to prove to me that that's actually a minimum.
Okay, and then I mean, you could argue that no other numbers work. I don't know how you can exactly prove that.
So we found this is extreme. It could either be a minimum or a maximum. But how can we show that which one it is?
I don't remember.
Okay, so a couple ways that we've done. You can do the number line thing. So find a bunch of, so we do this in terms of B. I know that 8 gave us, S prime of 8 was 0. So I could try this for 9 and 1, I guess.
So then you'd get, that would be a negative number for -1.
For 1, yeah, so this is negative.
And then for 9,
this is positive.
So then that would be your minimum, because if it was a maximum, it would be a positive on the left side, negative on the right side.
So something else you could do is take the second derivative of S, and that will give you 128 over b cubed. And any positive number you put in for b is going to give you a positive number there. So, and that's really that, and the number line kind of tell you the same thing, because the number line here, you can see that you're decreasing to something and then increasing afterward. That's kind of the definition of concave up.
Right. Okay. So do you think the number line then is more reliable than just taking the double derivative?
That's totally up to you. I mean, they both work.
Okay.
Or whatever you feel more comfortable with.
I'll probably just do the number line one.
Okay.
And then for number 7, I think I got most of this part right. So we'll take the derivative once, be 6x squared minus 6x minus 36.
And
then the double derivative would be 12x minus 6. And so I would first solve for the maximum and minimums, which is just means the derivative equal to 0. And then I think you can do you can take out a 6. So it makes it x squared minus 6x minus 36 or minus 6. And then from there you get x minus 3, x plus 2. And so your minimum and maximum values would be 3 and -2.
Well, those aren't, these are critical values.
Or critical.
Yeah.
And so, but the thing is, you can disregard the 3. as of right now because it's not in the interval.
Mhm.
And so then we can look at whether that -2 is a minimum or maximum using the number line rule. So then I would choose -3 and 0.
Mhm.
So for 0, it would be negatives. It would be a negative number. And then it would be for -3, it would be a positive number. So that's the minimum.
Okay. So
I
we
mean,
have a
the maximum. Sorry, that's the maximum.
local max at x equals -2.
Wait, shouldn't that just be the maximum though?
I have no man, maybe. So
Okay.
it's a local max, but where else? So you're looking for absolute minimum, absolute maximum.
Mm-hmm.
Those might happen at critical points, but where else might they show up?
Like just on the line, right? Or
What do you mean by that?
like if it keeps going, or like how do I describe it? There's some of those weird graphs where there's intervals where it's like it's split into two or three parts. I think it's just two parts, but it's like I don't know. I don't remember exactly, but
Okay. So your absolute extrema could happen at critical points. But like, what if you have a function that looks like this? So left end A, right end B. So your absolute max is going to be up here, which is going to be at a critical point. But your absolute min will be like, at
so
B
you
here.
also want to check the endpoints so as
Right.
well.
So you found a place where you're, that local max, that x equal -2, that might be an absolute maximum, but you don't know enough yet.
Okay, so as of right now, but we know it's just a maximum.
Yep.
Okay, and so then in that case, couldn't we just plug in -3 and 2 into the original equation?
Yep. So f of -3, f of 2. Let's get those.
So f of -3 would be -54. Yeah, -54, and then minus 18. Or sorry, minus 27. And
Okay.
then minus, all right, wait. And then it'd be plus 30, 90, 108 plus 10.
What was that you just said?
Oh, wait, is that what the final one should be?
I'm not sure. I think, what are you trying to find right now?
I was plugging -3 into the original equation for every x value.
Oh, okay.
So it'd be for -3, it'd be -54 minus 27 plus 108 plus 10. My calculator just died on me, so I don't have one.
Oh, okay. So that's 54. 37.
And
then f of 2 would be 16 minus 12. 14 minus 72, -58.
And then that would be minus 12, minus 72. Oh, you already said it. Okay, my bad. Okay, so then I think the best thing that we could do is check our local maximum then.
Yeah, you have to look at that one too.
So then that'd be -2, -16.
-16 minus 12.
Minus or plus 72 plus 10.
So that's 82, 54. Okay.
So then that is our local or our absolute max within this.
So absolute max here. And what's the absolute min?
And it has to be 2.
Yep. And just because we brought it up earlier, as long as you show me the X and Y value, I'm happy.
But we won't
yeah.
get full credit for it though. Right?
I mean, no, I want the full point. Sorry. I want, give me both coordinates.
Okay. Cool. So now that I don't know, maybe we could look at like the first, or could you send me test 1? And do you still have office hours tomorrow, by the way? Or
No, I don't.
okay. Are you free at all tomorrow, by the way?
No. But I'll be back on Zoom on Wednesday.
Yeah, I saw from what, like 7?
I think 8 to 9, something like that.
Yeah, okay. Is there any way that you could send me tests like a PDF of test 1 to kind of redo it and then
I'd rather not send out the electronic copies of the tests.
okay. But no, I totally understand that.
Yeah.
Okay. Then I think that's it. I don't think we have time for anything else.
Okay.
But yeah, is this gonna be posted on under like
Yeah, I'll post it in that exam prep area.
okay, cool. Sweet.
Yep.
Awesome. Thank you, Professor. I appreciate
of course.
all the help and covering both tests.
Yeah,
So,
no problem.
thank you. I'll see you Wednesday for sure.
All right, sounds good.
Okay, bye.